Yeah, 1, 1, 2, 3, 5, 8 is the sixth number in the list. So this is 8 phi plus, and then F5, what is that? 5. The fifth number in the Fibonacci list is a 5. So that's what the formula is. If you want to calculate a power of phi, you can use this formula that has Fibonacci numbers in it. So that's what this part where we were discovering that formula was pretty algebra intensive. We were doing all kinds of substitutions and distribution, combining like terms. So this is all stuff that I was pulling from your Math 105 or high school math background. It's a little algebra intensive, but the result, the purpose of doing all that work is that now we have this nice, neat little formula that we can use to calculate higher powers of phi instead of doing all the algebra. And then the very last thing is that in addition to the recursive formula, which if you remember, the recursive formula looked like this, that f sub n, any Fibonacci number, is equal to the Fibonacci number right before it, which is f sub n minus 1, plus the Fibonacci number 2 before it, which is f sub n minus 2. So that's a really simple, straightforward formula. Each number is the sum of the 2 before it. But we have also an explicit formula. So remember, the difference is a recursive formula uses previous numbers in the list, and an explicit formula only uses n. So we have this crazy looking explicit formula. You might recognize 1 plus root 5 over 2, that's phi. The golden ratio is in there. I'm not going to hold you, you're not going to have to use this. Okay, I'm not going to make you use this to calculate Fibonacci numbers. I just wanted to show you that it exists because it's so, it's just such an interesting difference in that this one's so simple and this one's so complicated, but they give you the same thing. If I wanted to calculate, say, the 200th Fibonacci number, it would take me a long time using the recursive rule because I'd have to calculate every Fibonacci number from 1 to 200 to get it. Or I could just plug a 200 into this formula and get it right away. It's just that this one is kind of ugly. No. Okay, so that finishes up our discussion of Fibonacci numbers and the golden ratio. Moving on to class 15. Okay, so moving on to class 15, we're going to talk about gnomons and nature. So we're going to have to do a quick little review of some geometry concepts before we jump into gnomons. Anybody know what it means for two objects to be similar? Oh, okay. Same proportions but different sizes. So same shape, different sizes, right? So in another way, one object would be a scaled version of the other. Okay, so when you scale something down or scale it bigger, those two objects are similar. So if I draw this triangle and this triangle, they'd be similar. Okay, so they have the same shape. One's just a blown up version of the other. The symbol for similar is that little squiggly line. One little squiggly line. So these two triangles, 3, 4, 5, and a 6, 8, 10, are they similar? Yes. What is the scale factor? Yeah, I doubled all the measurements from the little one to the big one. So this is, yes, they're similar. Scale factor is 2. So let's look at the perimeters of the two triangles. The perimeter of the 3, 4, 5. Perimeter is just when you add up the distance around. So 3 plus 4 is 7, plus 5 is 12. And the perimeter of the big triangle, 24. So what's the scale factor from the perimeter of the small one to the big one? 2. Scale factor is still 2. So perimeter scale factor is 2. All right, let's look at the areas. The area of a triangle is 1/2 base times height. And in a right triangle, we can use the legs that are perpendicular to be the base and the height. So my base would be 4 and my height would be 3. So what's my area? 6. Good. And then what's the area of this bigger triangle? 1/2 times 6 times 8. 6 times 8 is 48, and half of that is 24. Yeah. So I heard a lot of people saying 12, and I think that you were trying to follow the pattern of the scale factor, right? You said, well, the scale factor is 2. All the sides get doubled, the perimeter gets doubled, the area should get doubled, right? But it turns out the area... Yep. Doesn't matter. Yeah. Yeah, you can do multiplication in any order. So my area went from 6 to 24, so it increased by what factor? 4. I multiplied by 4. So my area scale factor is different than my length and perimeter scale factor. In fact, it is the perimeter and length scale factor squared. And that will always be the case. So area scale factor will always be the length scale factor squared. For any shape, not just for a triangle. Okay, so let's suppose that these two triangles are similar. I want to find the other two sides of the big triangle as well as the perimeters and areas. Cross out this ratios of the. I just want the two triangles, perimeters, and areas. So I want you to discuss in your groups. See if you can come up with the missing side lengths and the area and perimeter of each triangle. Okay, so one of the great things about dealing with similar figures is that there's more than one way to solve the problem. Okay, we can use the scale factor or we can write proportions. So let's start with the scale factor. My length scale factor is what? Is 5. How did you figure that out? Yeah. Yep. So this one's a 3 and this one's a 15. So my scale factor has to be 5. I enlarged everything by a factor of 5. So that means that this 4, when I enlarge by a factor of 5, will become a 20. And this 5 will become a 25. And then the perimeter of the little guy is 12, which means the perimeter of the big triangle, I could just use the scale factor. 12 times 5 is 60. And I can double check it by just adding up the 3 sides of my bigger triangle. 15 plus 20 plus 25. The area of my little triangle is 1/2 times 3 times 4, which is 6. The area of my big triangle should be 6 times what? 25, right? The scale factor for length, but squared. So this is going to be 6 times 5 squared. 6 times 25 is 150. And we can verify that area by just doing a calculation on this triangle. 1/2 times 15 times 20 is 150. So we got all the answers by using the scale factor. Let's start over, and I'm just going to show you another method to get these answers. So I have a little 3, 4, 5, and then I have a bigger triangle with a 15. It's not quite to scale. It's better. All right, so let's say I call this side x. That missing side we'll call x. I can write a proportion where I put short to short equals middle to middle, right? As long as you put the corresponding pieces, you could do short to short, long to long. Middle to middle equals long to long, or short to short equals long to long. Whatever, as long as you have corresponding pieces on the top and the bottom, you can write a proportion. So the short side of one triangle to the short side of the other should equal the middle side of one triangle to the middle side of the other. And we set up this proportion that we can solve by cross multiplying. So we have 3 times x equals 15 times 4. Divide both sides by 3 and you get x is 20, which is exactly what we got when we used the scale factor of 5. So this is just another way to solve this problem. We could do short to short equals long to long. So I would say 3 to 15 equals 5 to what? We'll call the long side of the big triangle y. And then I can cross multiply, so I get 3y equals 15 times 5, which is 75. Divide both sides by 3, and you get y is 25. So just another way to set up a solution to this problem. So in my experience, I found that the split is kind of 50-50 in people that like this way using the scale factor and people that like this way using proportions. So whatever feels more comfortable to you, go ahead and do that. All right, so now we're going to get into a new definition, something called an Omen. So this sounds really kind of wordy. Once I show you an example, I think it'll be much clearer. But the definition of an Omen is a figure, an Omen to a figure is another figure which, when you attach it to the first figure, you get a new figure similar to the original figure. Whoa, I used the word figure way too many times in there, right? So let me do an example for you. I have a rectangle, a 1x2 rectangle. So let's imagine I'm a carpenter, okay? And I need to cut out a big rectangular piece of plywood. And I cut it out and it's 1 feet by 2 feet. And then I say like, shoot, I meant to cut out, I meant it to be twice as big, right? I want actually, my ratio was supposed to be bigger than that. I want to double the size of this thing. Rather than throwing this away, I'm going to cut out an L-shaped piece of plywood that I can glue to that thing to make the dimensions that I really want. Okay, so I really want this thing to be 4x2. So I need to go like this. Oops. So this blue L that I've glued on to my mistake, that is called an omen. Okay. Because once I glue it together, the original, my 1x2, is similar to the glued together thing. So the L that I put on here is called an omen. So my resulting rectangle after gluing them together is twice as big as my original rectangle. So if I make this 1 and this 2 and this 2 and this side is 4, that's the L that I needed to make to fix my mistake. Does that make sense? Okay. So the L-shaped piece that we attached to the original is called a gnomon to the rectangle. For rectangles, it's also possible to add a gnomon that's also a rectangle. It doesn't have to be an L shape. And in fact, if I'm a carpenter, maybe I prefer to do this because cutting an L is a pain in the butt, right? So let's try to add a gnomon to this thing that's another rectangle instead of an L. So the resulting rectangle I want is going to be 2x4, right? I made a 1x2. I want it to be twice as big. It has to be 2x4. I happen to already have a side of this rectangle that's 2 feet. So if I just extend it this way, I could end up with a rectangle that's 2x4. If I put 3 feet on this edge. So if I make that 3x2 and glue those together, I end up with a rectangle that's 2x4, which is what I want. Now I just have to turn it on its side. So does that make sense? So it's just 2 different ways that I can correct my mistake. Okay, I could cut out an L, or I could cut out another rectangle, glue them on, and in this case, I have to turn this on its side to make it look like the original. So what kind of shape would be a gnomon to a circle?
A ring.
Yep, a ring. So if I had cut out a circle and I said, oh shoot, it's too small, if I want to glue on another piece to make it bigger, I'd have to glue on a ring. So any triangle that has angles 36, 72, 72 has a family of gnomons. You can just continue to draw them over and over again. And I'll show you how to do it. So we're going to attach to this 36, 72, 72 triangle a 36, 36, 108 triangle. So those are the measures of the angles. So on this triangle, if I continue this line so I just get a straight angle at the bottom, what is the measure of that angle? 108. Yeah, because a straight angle has how many degrees? 180. And I already have 72 of them accounted for here. So if I do 180 minus 72, I get 108. And then up here, I'm going to copy this 36-degree angle. So I have another 36-degree angle here. And then I should draw this so that it's nice and straight. So if I extend this down till they touch, what is that third angle of this triangle that I've drawn? 36, because the 3 angles of a triangle have to add up to what? 180. So it's, maybe you remember that from a geometry class that you took at one point in your life. The three angles of a triangle add up to 180. So 108 plus 36 plus what gives me 180? Another 36. Okay. So this green triangle that I've attached to the original blue one is an omen to the original blue one because I have made, what is 36 and 36? 72. So I've made another triangle that has two 72-degree angles and a 36-degree angle. So if I were to take this connected figure, the blue and green glued together, and rotate it so that this is the bottom, it would look exactly like my blue one, just blown up. Do you see it? You got to do some like manipulating in your brain. So I can keep doing this over and over, right? So I would just, now I'm going to extend this line on the 72-degree angle, and I get 108. Copy the 36, and draw these till they connect. And this would be a 36. And now the big outer triangle, this big red triangle, is similar to this original blue triangle. We have a 72, 72, 36 triangle. Yeah. So since I'm a terrible artist, I'm going to try to, I have a little animation of this that I'm going to show you. I have a 36, 72, 72 triangle. I can create an omen by putting the 108, 36, 36 triangle onto it. So if this side is the bottom, then it's going to be similar to the original green one. And then I can put on another one and another one. Oh, thanks. So I just keep building this bigger and bigger triangle. So right now it's rotated, but this large triangle is similar to my original little green triangle. So this triangle is also called a golden triangle because if you measure the length of one of these longer sides and say, let's call that X, and we can call this one Y. If you do the longer side over the base, you get the golden ratio again. That thing that was related to the Fibonacci numbers that we discovered last class, 1.618. No matter what size this triangle is, whether you have a big one or a little one, if the angles are 36, 72, 72, the ratio of the longer side to the short side is 1.618. It's weird how that number keeps popping up. So we've already seen that every rectangle has an L-shaped gnomon. Sometimes you can make a rectangular shaped gnomon. We did one of those. Some very special rectangles have a square gnomon. So I want to figure out what kind of special rectangle can be completed with a square. So if I have this rectangle, I'm going to have one side be 1 and the other side be x. And I'm going to attach a square onto the bottom of it so that I have an x by x square on the bottom. And then I turned it on its side over here so that you could see the similarity, so that you could see that these are now the same shape and one's just a blown up version of the other. They have them sitting in the same orientation. So in order for the x by x square to be a gnomon to this rectangle, this large outer shape, the glued together rectangle, has to be similar to the little rectangle, which means that the sides have to be in proportion. So I'm going to write a proportion: short to short equals long to long. Okay. So if I look at the little rectangle, what's the length of the shorter side? 1. And in the green glued together rectangle, what's the length of the shorter side? X. So I'm going to have 1 over X equals long to long. So the long side of this one is X. And what's the long side of this one? X plus 1. Does that proportion look familiar? We solved this exact proportion last class when we were talking about how to make the prettiest division of a line segment. When you cross multiply, you get x squared equals x plus 1. And this is an equation we solved before. It's a weird S, sorry. We solved using the quadratic formula. And what was the solution? Anybody remember? Yep. 1 plus the square root of 5 over 2, which came out to be about 1.618, which is the golden ratio phi. So the moral of this example, right, is that only a rectangle, only certain kinds of rectangles have square nomens. Okay? And that is a golden rectangle. So the special rectangles above that have square nomens are called golden rectangles. A golden rectangle is the one where length divided by width is phi. Or width divided by length, doesn't matter. Long side divided by short side has to be phi to make a golden rectangle. And these are the only kinds of rectangles that have square nomens. So in my rectangle up here, x turned out to be 1.618. So the length divided by the width, 1.618 over 1, is in fact 1.618. The golden ratio. So a golden rectangle is one where the ratio of length to width is phi. What do you think a Fibonacci rectangle is? Any guesses? We can make a spiral of Fibonacci rectangles, but it's just a rectangle whose length and width are consecutive Fibonacci numbers. So a 1 by 1 square is a Fibonacci rectangle. A 1 by 2 rectangle is Fibonacci because 1 and 2 are consecutive numbers in the Fibonacci list. Or a 2 by 3, or a 3 by 5. Oops, I ran out of room. Or a 5 by 8. Those are all Fibonacci rectangles. Are Fibonacci rectangles golden rectangles? Is the length divided by the width the golden ratio? For all of them? Only really big ones, yeah. Because here the length divided by the width is 1, right? That's not really close to 1.618. But as we go further out in the Fibonacci list, one of the things we discovered last class was that the ratio of the bigger number to the smaller number is approaching 1.618. So as you go further out in the list, they become more and more golden. Okay. So as the rectangles get bigger, I should say as the Fibonacci rectangles get bigger, they get more golden. So I'm going to show you another thing in Geometer Sketchpad about how to use Fibonacci rectangles to make a spiral. Okay, so I'm going to start with a little square, a 1x1 square. So I'm going to start really little. And then I'm just going to keep adding squares. So this is a 1x1, right? If I put another square on it, it's the same size. Now I have a 1x2 rectangle. Does that make sense? So this, I added a Omen to the original one. So I have a 1x1, I added another 1x1, and now I have a 2x1. So I've created the second Fibonacci rectangle. I can create the third Fibonacci rectangle by putting another square on here. So the whole outer shape is now 2x3, because this is length 1 and this was length 2. And 2x3 is a Fibonacci rectangle. So then I'll do another one. I'm going to put another square on here, 3x3 square. And now my rectangle is now 3 by, what is this length down the bottom? 5, because this is 2 and this is 3. And I can just keep adding squares as I work my way around. And I'm going to move this thing. So that I can add a little bit more. Put one more up here. And all right, so I'm basically out of room. Can't do anymore. So I've created this spiral starting on the inside. I'm working my way out and I get this spiral. Let's spiral. Is that the right one? Yeah, I did the wrong one to start. No, that's not right either. There we go. So I can build this spiral through all these squares that I made. And you get this green spiral, which looks an awful lot like a lot of things that you find in nature. Looks like a snail shell, nautilus shell. What, somebody said some? Oh, okay. We see tons and tons of things in nature that have this shape, and that is not a coincidence. Because some organisms grow by adding new pieces while maintaining their shape. So that's not us. Like, so we are constantly having cells die and making new cells, right? So there isn't a piece of me that has existed since I was born, right? Whereas a tree, when you cut down a tree and you look at the rings, the inner part of the tree is older than the outer part of the tree, right? The further you go in, the older the wood is inside the tree. So some organisms grow like a tree, where they just keep adding more and more pieces to themselves. And some organisms grow like we do, where parts die and new parts grow. Okay. So if you grow by adding new pieces onto yourself and keeping all the old parts too, and you maintain your shape while you do it, then the new pieces that you add on have to be nomens to your original shape. Does that make sense? Okay. So examples would be a nautilus shell or a tree, right? Because a tree adds nomens because the nomen to a circle is a ring. So trees add rings to maintain their shape, and those are nomens. But also the nautilus shell, pine cones, and sunflowers do this also. And that's why in pine cones and sunflowers you see spirals. Okay, so cool. We have some time. So I have some really interesting videos to share.